Okay, so here in this video, we're going to learn another method of approximation for a definite integral. So let's go back and review what we have so far. If we took a function like this from a to b, and we broke it up into equal partitions, we either chose the left endpoint of each subinterval. So from here to here, this subinterval, this would be the left endpoint. From here to here, this would be the left. From here to here, the left. And from here to here, the left. So we have 4 equal subintervals, and we chose the left endpoint. We took that endpoint, we put it into the function to get the height, and we added them all up. Or we took the right endpoint in each subinterval. So from here to here, this would have been the right. From here to here, this would have been the right. From here to here, the right. And from here to here, the right. Or we also improved upon that approximation by taking this right here and dividing it in half. And that was called the midpoint. So we would add the ends and divide by 2. That would be our midpoint value. Put that into the function to get the height. And we would add up all of those. Okay, so again, what we've done so far was either the left, the right, or the middle. Now there's another way to improve upon this approximation. So let's consider a graph like y equals x squared plus 1 from 0 to 4. And when x is 0, y is 1, and when x is 4, we would get 17. So the shape of it is a parabola concave up like that. And we're going to break it up into, say, 4 equal subintervals. So this would be in half, and we'll cut it in half again and again. But this time we're not going to approximate the area under the curve bounded by the x-axis by using a left, right, or middle. We're going to use a different method called the trapezoidal rule. So how do we come up with the approximation using trapezoids? Okay, so first let's draw in some trapezoids. So from here to here, I'm going to connect these 2 endpoints and form one trapezoid. And then from here to here, I'm going to form another trapezoid. And then from here to here, I'm going to form another trapezoid. And from here to here, I'll form another trapezoid. So I've got 4 trapezoids. This being 1, 2, 3, and 4. Like when I was developing the rule for the left, right, and the middle, I drew in rectangles. And we said that the area of each rectangle was delta x, the width of the subinterval, times the height, whether we chose the left endpoint, or the right endpoint, or the middle endpoint to put into the function to get that y back. That's what we did. We drew the rectangles for the rectangular approximation. So for a trapezoidal approximation, it makes sense that we would draw trapezoids. And you can see that already we're improving upon our approximation by using trapezoids rather than sometimes just a rectangle, either the left, right, or the middle again. So what's the rule then for finding the area using the trapezoidal rule? Okay, well we know that the area of a trapezoid is 1/2 times the height times the sum of the bases. So that is our area formula for a trapezoid. So if this is x is 0 right here, and I'm breaking this up into 4 equal subintervals. Yes, and the assumption is here we're breaking it up again into equal subintervals. So the width of each subinterval, delta x, is b minus a over n, and b is 4, a is 0, and n is 4 in this case. We'll use 4 equal subintervals. So delta x, for simplicity's sake, is equal to 1. So that means that the x's, starting with 0, I'm going to add delta x, get 1, add it again, 2, add it again, get 3, and then get 4. So these would be my subintervals if I were doing the left, right, or the middle. And of course, if you remember, to find the middle, we'd have to add the ends and multiply by half. So that'd be 1/2, 3/2, 5/2, and 7/2. But again, we're going back to the trapezoidal rule. So each of these is worth a delta x right here. And each of these are worth 1. So this would be 1, 2, 3, and that would be 4. So if you look, just take this one right here as a trapezoid, this right here being my trapezoid. These are my bases. These are the parallel sides. So like right here, these are the parallel sides in that trapezoid. This would be the height. And the height in every trapezoid is delta x. So far for the trapezoidal rule, what we have here in this trapezoid, we have 1/2 times delta x times, this right here is my first x value. I can call that x sub 1, this being x sub 2, x sub 3, x sub 4, and x sub 5. So my first x value, the height of this side, is f of x sub 1, plus the height of this side would be f of x sub 2. Now for this trapezoid, it would be 1/2 times the height, which we know is delta x. So we can just put that as delta x, times, okay, well this height right here is f of x sub 2. And this height right here is f of x sub 3. Now for this trapezoid, that would be 1/2. The height is delta x times this height, this base, is f of x sub 3. And this base is f of x sub 4. Plus, the last one's 1/2 times delta x times the last one, again this is delta x, this base is f of x sub 4 high, and this base is f of x sub 5 high. So you can see that we can clean this up. What we can do is, we can take out the 1/2, because that's common in each of these, so we can take that out, and we can also take out the delta x, because that's common in each. Because remember, in this case, all the subintervals were of equal length, or equal width, if you will. They were of equal width. So here, I have 1 f of x sub 1, and then I've got 2 f of x sub 2's, and then I've got 2 f of x sub 3's, plus I've got 2 f of x sub 4's, and 1 of f of x sub 5. So this is the rule right here for trapezoidal. It is 1/2 times delta x times, you only get 1 y of the first, and you get 1 y of the last. And we would double all the y's in between. I mean, you could see that generalized, that's the pattern that's going on here when we have equal subintervals. Okay? So delta x is here because it's the same, it's a common factor because it's the same for each subinterval. Because this base is not shared with another trapezoid, we only have one of them. And because this base right here is not shared with any other trapezoid, we only have one of those. But all of these in between are shared between two trapezoids, so we have 2 of those y values. So I like to say, for simplicity, the trapezoidal rule, again, when you only have equal subintervals, is 1/2 times delta x, 1 of the first y, 1 of the last, double all the y's in between. So let's go back now and attempt by doing a problem, putting it all together. So suppose again we have y equals x squared plus 1, and we're on the interval from 0 to 4. And n equals 4. We want 4 trapezoids. So as we saw before, but I did not complete that example, we'd have 4 minus 0 over 4, and then at delta x is 1. So my x's are 0, 1, 2, 3, and 4. In this case, all the x's get used. With the left or the right rectangular approximation, one of the x's always got left out. You know, if we were doing the left of each subinterval, the 4 would have gotten left out. If we were doing the right of each subinterval, the 0 would have gotten left out. But in a trapezoidal rule, all of the x's get used. Okay, so since, again, delta x is the same for each subinterval, we can use our shortcut. So the area by trapezoidal will be 1/2 times 1, because that's what delta x is, times 1 of my first x's plus 2 of my second x plus 2 of f of 2 plus 2 of f of 3 plus 1 of my last. Okay? So again, the first x and the last x, everything else in between gets doubled. So this would be equal to 1/2 times 1 times, put 0 in, I get 1. 1 in, I get 2. 2 in, 4 is 1 plus 1 is 5. 9 plus 1 is 10. 16 plus 1 is 17. And now I'd have 1/2 times 1 times 1 plus 4 plus 10 plus 20 plus 17. And I'd get here 1/2 times, that's 30, 35 plus 17. Looks like to be 52. Divided by 2 is 26. So how does it compare to the actual answer? We should know that the actual answer is from 0 to 4 of x squared plus 1 dx. And that antiderivative would be x cubed over 3 plus x from 0 to 4. So I put that in, I'd get 64 thirds plus 4, that is plus 4, minus 0 would just be 0. So then, how does that come out? Well, I get 64 plus 12 over 3, and that comes out to be 76 divided by what here? 3. And that would give us here, 3 goes into 7 twice, 1's left over, 3 goes into 16, 5. So that's what? 25 and 1/3. So we could see here that our approximation is greater than the actual value. The actual value is 25 and 1/3. The approximation is 26. So why is that the case? Well, if we take a look at the sketch of this function on the interval from 0 to 4, x squared plus 1 like I had before from 0 to 4, why the approximation is greater than the actual value is because when I constructed my trapezoids, a portion of it was outside the enclosed region. So of course we ended up with more area than what we should have. And the reason why that is because this function, x squared plus 1, is concave up on the interval from 0 to 4. That's very important. When we talk about a left Riemann sum or a right Riemann sum over approximating an integral or under approximating an integral, what we use is whether the function's increasing or decreasing. So if we were doing a left approximation on this interval, then the left would have been an underestimate because f is increasing on that interval from 0 to 4. And we know it's increasing because f prime is 2x, f prime is greater than 0 on the interval from 0 to 4. But for trapezoidal, we do not look at whether it's increasing or decreasing. We look at the concavity of the function. And that, of course, refers to the second derivative. That would confirm that this function is concave up on that interval. So if f prime equals 2x, f double prime equals 2. F double prime is always positive here, but in particular it's positive on the interval from 0 to 4, which means f is concave up, so the trapezoidal rule overestimates the actual value. Okay? It overestimates the actual value. So what I try and tell students how you can remember this is trapezoidal is up and over. If it's concave up, the estimation will be over the actual value. If it is, because remember the actual value was 25 and 1/3. If it's concave down, then it will be down and under. Okay? So again, if the homework's asking you to state whether or not the trapezoidal rule is an overestimate or an underestimate, you have to proceed to the second derivative and look at the sign of the second derivative on that interval. If it's positive, then the function is concave up, in which case then the trapezoidal rule is an overestimate. If the second derivative is negative on that interval, then the trapezoidal rule is an underestimate of the actual value. Up and over, down and under. And that works for equal subintervals here, the trapezoidal rule.